The moment the universe first burst into light is one of the most awe-inspiring events in existence, shaping everything from the tiniest particles to the vast cosmos we observe today. It's a story of emergence, of a spark that ignited reality itself, and understanding it can unlock the deepest secrets of our origins. Stick around, because what happened at that instant could change how you see everything, past, present, and the infinite future ahead. The birth of the universe, the Big Bang Theory. The universe's inception is traced back to a moment when all matter, energy, space, and time were compressed into an infinitesimally small point known as a singularity. In an instant, this singularity began expanding rapidly, marking what cosmologists call the Big Bang. It wasn't an explosion in space, but rather an expansion of space itself. From this singular point, the universe started swirling into existence, setting into motion all the physical laws and fundamental particles we observe today. This initial burst of energy was so intense that it produced a hot, dense state that would gradually cool and evolve over billions of years into the cosmos we see now. Immediately after the Big Bang, the universe was filled with a nearly uniform hot plasma of particles, including quarks, electrons, and photons. Because of extreme temperatures, these particles could not form atoms yet. Instead, they moved freely within this glowing, opaque fog, a universe in a state of chaos and warmth, shielding the early universe from any light that might escape. As expansion continued, the universe cooled, allowing particles to combine into simple atoms, predominantly hydrogen and helium. These elements served as the building blocks for all future stars, galaxies, and planets, emphasizing how the process of cooling and gradual matter assembly was crucial in shaping cosmic evolution. The moment when light first became able to travel freely through space is often considered a pivotal event. Once the universe cooled enough for electrons to combine with protons and form neutral atoms, photons, particles of light, could travel unimpeded. This epoch is called recombination, and it produced a faint glow that we now detect as the cosmic microwave background, CMB. This radiation provides a snapshot of the universe at that early stage when it was roughly 380 years old. The CMB is like a faint echo of the initial moment of light, offering valuable insight into the conditions of the universe at its infancy. Detecting and analyzing this radiation allowed scientists to confirm the Big Bang Theory and refine our understanding of the universe's early moments. In essence, the story of the universe's birth intertwines rapid expansion, cooling, particle formation, and the emergence of light, all occurring within the first few moments after the initial singularity. The process set the stage for all cosmic structures to develop over eons. While the fine details continue to be studied, this foundational understanding reveals how the universe's first light was born out of an unimaginably dense and hot state, giving the cosmos its grand beginning and a course that would unfold over billions of years into the complex universe we explore today. Emergence of light, from singularity to photons. At the moment when the universe burst into existence, it was a chaotic, seething expanse of energy, temperatures skyrocketing beyond comprehension. In these early instants, the universe existed as a near-infinite density point, what scientists term a singularity, before the rapid expansion known as the Big Bang. This initial expansion set the stage for the birth of light. Initially, everything was so hot that photons, particles of light, could not travel freely. They were constantly scattered by particles, preventing any form of coherent light from emerging. Conditions were akin to an opaque plasma, dense with protons, neutrons, and electrons, and photons bounced randomly, unable to escape or give rise to the kind of light we recognize. As the universe expanded, it cooled down dramatically. Temperatures dropped from hundreds of billions to thousands of degrees, allowing protons and neutrons to combine into the first atomic nuclei. But despite this cooling, the universe remained too hot for stable atoms to form initially, leaving photons still tightly trapped in a dense, ionized fog. It wasn't until the universe continued its expansion and cooling that a critical moment occurred, around 380 years after the Big Bang, when electrons slowed enough for protons and electrons to combine into neutral hydrogen atoms. This epoch, often called recombination, marked the moment when photons could finally travel unimpeded through space, effectively crossing the universe for the first time without being scattered. The transition from an opaque plasma to a transparent universe was a pivotal event in cosmic history. Photons, once fleeting and constantly rescattered in a dense environment, could now stream freely across vast distances. This released a flood of light, a faint glow that we now observe as the cosmic microwave background radiation. It is a snapshot of the universe at that primordial moment, a relic that offers a window into the very earliest phase of light's existence. The photons emitted during recombination have been traveling through space ever since, stretching and shifting with the expansion of the universe to become the microwave background we detect today. This emergence of light from the depths of the early universe symbolizes a fundamental transition, the collapse of primordial chaos into a cosmos where light itself became a messenger of history. It embodies the universe's journey from a state of absolute darkness and chaos into one filled with radiant energy, structures, and eventually, life. Photons that originated in that first bright flash continue to influence the universe, shaping galaxies and stars, guiding cosmic evolution. Their story is one of resilience, escaping the molten, tangled chaos of the past to become the steady, measurable beacon that unlocks the universe's deepest secrets. The journey of the first light through cosmic evolution. The emergence of the first light marks a pivotal moment in cosmic history, often described as the universe's initial burst of visible energy. After the Big Bang, the universe was an extremely hot and dense plasma composed mainly of protons, neutrons, and electrons, with photons constantly scattering off free particles. As the universe expanded and cooled, it reached a point where protons and electrons could combine to form neutral hydrogen atoms, a process known as recombination. This transition allowed photons to travel more freely. For the first time, light could move unimpeded across vast expanses of space. This moment is often called the decoupling epoch because photons decoupled from matter, leading to the release of the universe's first faint glow of light. This primordial radiation is what we now observe as the cosmic microwave background, CMB. The CMB provides a snapshot of the universe when it was just 380 years old, an incredibly young cosmos in astronomical terms. Its discovery was groundbreaking because it confirmed key aspects of Big Bang cosmology and offered a glimpse into the conditions that governed the universe's earliest moments. The CMB's faint glow is remarkably uniform, but small temperature fluctuations, on the order of 1 part in 100, served as seed points for the large-scale structure we see today. These minute variations grew over billions of years into galaxies, clusters, and superclusters, all stemming from these initial imprints. The journey of this first light through cosmic evolution was far from static. As the universe continued expanding, the faint photons of the CMB cooled from their initial high-energy state, stretching into microwave wavelengths due to the cosmological redshift. Over millions of years, as matter began to clump under gravity, regions of higher density started to gravitationally attract surrounding matter, leading to the formation of the first stars and galaxies. Light from these early stellar nurseries has traveled through billions of years, often interacting with intervening gas and dust, but much of it retains information about the universe's infancy. The study of this ancient light, via telescopes monitoring the CMB and distant galaxies, has fundamentally reshaped understanding of cosmic history and the processes that sculpted our universe. The path of the first light encapsulates an incredible narrative, from the primordial fireball through a universe filled with veiled darkness to the dawn of stars and planets. Each photon that travels across cosmic time carries clues about the conditions of the universe at its earliest stages. Scientific efforts today aim to uncover the finer details embedded in this ancient glow, such as subtle polarization patterns and minute temperature variations, to deepen understanding of phenomena like inflation and dark matter. In essence, the journey of the first light is a celestial voyage that begins in the very moment of creation and continues through the expansive, evolving tapestry of cosmic history. Implications of the first light for our understanding of the cosmos. The first light emitted in the aftermath of the Big Bang, often called the cosmic microwave background, CMB, represents a pivotal moment in understanding the universe's origins. This faint glow, observable today through sensitive instruments, offers a direct window into a time when the universe was merely 380 years old, an era when electrons and protons combined to form the first hydrogen atoms, allowing photons to travel freely for the first time. Analyzing this ancient light has revolutionized cosmology, providing insights that shape how we interpret the universe's structure, composition, and evolution. One of the most profound implications of this initial illumination is the way it validates the Big Bang theory. The uniformity of the CMB across the sky aligns with predictions made by models of a rapidly expanding universe from a hot, dense state. Tiny fluctuations within this background radiation, the minute temperature differences, serve as the primordial seeds of all current cosmic structures. These fluctuations help scientists trace the formation of galaxies, galaxy clusters, and large-scale filaments. The pattern and scale of these anisotropies reveal clues about the universe's overall density, dark matter content, and the influence of dark energy, which accelerates cosmic expansion. Furthermore, the first light has opened avenues for understanding fundamental physics beyond the reach of terrestrial experiments. Since conditions just after the Big Bang are unlike anything we've produced in laboratories, the CMB provides evidence about particle interactions, inflationary mechanisms, and neutrino properties during the universe's earliest moments. For example, detailed measurements have constrained models of inflation, rapid exponential expansion, and suggested that quantum fluctuations during that period were responsible for the tiny temperature variations we observe. Such insights help refine theories that attempt to unify gravity with quantum mechanics, moving us toward a more comprehensive picture of fundamental forces. Finally, the implications extend into the ongoing quest to determine the universe's ultimate fate. By examining the properties of the cosmic light from its infancy, scientists infer the rate of expansion and the nature of dark energy. Precise measurements of the CMB, combined with large-scale surveys of galaxy distributions, allow for more accurate estimates of the Hubble constant. Discrepancies between different measurement methods are fueling debates and prompting new theories about unknown components or physics that might influence cosmic evolution. In essence, the first light acts as both a historical record and a diagnostic tool, guiding us toward more mysterious questions still awaiting answers. Usnovnoy, Rusgil 5. In the earliest moments after the universe's inception, a staggering transformation took place, what we refer to as the emergence of the first light. This event marks the transition from a dense, opaque fog of particles into a universe increasingly transparent to radiation. Initially, the universe was so hot and dense that photons, the fundamental particles of light, were constantly scattered by electrons and protons in a state akin to a blistering plasma soup. This intense coupling kept light confined, preventing any form of visible illumination or coherent signals from traveling freely. As the universe expanded, it cooled rapidly. When temperatures dropped enough for protons and electrons to combine into neutral hydrogen atoms, a process called recombination, photons suddenly found a new environment where they could travel unimpeded. This release of trapped radiation is known as the cosmic microwave background, a faint glow still observable today, providing us with a snapshot of the universe when it was just around 380 years old. This event didn't generate visible light as we know it, but rather thermal radiation that stretched into microwave wavelengths. It is the oldest electromagnetic signal we can detect, offering invaluable clues to the universe's initial conditions. The emergence of this primordial light ignited a cascade of cosmic developments. It set the stage for the formation of the first stars and galaxies, which began as tiny density fluctuations amplified by gravity. When the earliest stars ignited, their nuclear processes emitted intense radiation, some of which continued to travel across the cosmos, shaping the cosmic landscape we observe today. These early sources of light gradually cleared the remaining fog of ionized particles, leading to a universe that became progressively more transparent and luminous over time. Their light is weak yet persistent, traversing billions of light years, revealing a universe that has been evolving ever since that initial flash of illumination. As we reflect on the first light, we're reminded of that incredible moment when the universe first ignited into existence, casting the very first glow that would eventually shape everything we see today. We explored how this primordial light marked the birth of time and space, revealing the universe's early secrets and setting the stage for everything that followed. It's awe-inspiring to think about how this tiny spark laid the foundation for galaxies, stars, and ultimately our own existence. Thanks for joining us on this cosmic journey. If you found this glimpse into the universe's origins as fascinating as first did, be sure to stay tuned. There's so much more to uncover about the universe's mysterious beginnings and what lies ahead. Keep looking up, and first we'll see you in the next adventure.